Now let's look deeper into atoms and elements, right? We need to actually understand, especially matters concerning the electrons. So here we are going to see why there is an improvement in the electronic configuration. But you don't know, from high school, from junior high school, you learned a way of arranging electrons inside the atoms. But when you go to senior high school, the model change, the process of doing that change. But then now we are going to understand why there's that improvement in this electronic configuration. All this discussion revolves around one thing, that is discussing around the electron, right? So we are going to be discussing majorly things around the electron. But then let's do some recap on the electron in general. We said the electrons are negatively charged particles. The electrons are located on the shells or orbits of the atom. They have negligible mass, and then they take part in the chemical reactions. They are the one that take part in the chemical reactions. Let's go out from the electron and look at an atom in general. This is a sample atom, and then this is how it look like. And then let's label them. Inside it, we have the nucleus, as usual. Then the things surrounding in the circle, the blue circle surrounding it are the electron shells or orbits. We call them orbit. We can call it energy levels. We call them energy levels as well. Those are the terms that we'll be using more now, right? And then we have the black dots, which are the electrons themselves. So this is the general overview of a basic atom and a basic electron. So now let's focus a bit on the shells. Let's focus a bit on the shells. The shells that you are seeing, the blue circles, right, from the inside, from the one closer to the nucleus to the one outside, they are labeled in that order. And then that label starts with letters like K. So the first one, you have the K shell, right? The K shell is the very first shell closer to the, this time I made it yellow so that you can actually distinguish what I mean. So there's a K shell, we refer to the first one. And then the next one is the L shell. And then the last one is the M shell. So these are not all, they continue from K, L, M, N, O, P, Q, R, S, T, right? They follow the alphabetical order. But then the basic one, you know, you have to start with the K, L, M, N. Any additional shell follows that alphabetical order or reading or sequence, as we know in English, but we start from K. Okay. Now, what is electronic configuration itself? So in basic terms, electron configuration is the arrangement of electrons in an atom's energy levels, or arrangement of electrons in the energy levels or shells, right? If you look at this one in general, you can see the electrons are the black dots on the various shells. The electrons are not placed on these shells in any manner or just like that. They follow a specific rule. And then that rule of that process of arranging them is what we call the electron configuration. It's the arrangement of electrons in an atom's energy levels or shells or orbits, as we said. Now, let's look at what we were taught in junior high school. In junior high school, we were taught this method, the 2-8-8 approach. This is what we were taught, how to flow the electrons inside the shells, right? We were told that the first shell takes 2 electrons maximum, and each of any additional shells that follow takes a maximum of 8 electrons as well. So these are separated by commas in rotating format. So it's like 2, 8, 8, 8, 8. But the very first one is 2. The rest are following 8, 8, 8. That's why I call it the 2-8-8 approach. That's what we were taught in senior high school. But let's look at an example. Let's revise that looking at an example. So let's focus on potassium, right? Potassium has 19 electrons in total. So it has 19 electrons in total, right? So the first shell takes 2 electrons. We are following the 2-8-8 approach. So first shell takes 2 electrons. So that's 2 electrons. They write the configuration, you write the 2 down. You update the configuration 2 down. That's the very first one. Then you proceed. The remaining electrons to enter the shell. We have 19 electrons, but we have already configured 2 already. So 19 minus 2 give us 17. So it's left with 17 electrons more to fill, right? So now we move on from the first shell to the next shell. So the next shell with the second shell will now take 8 electrons because we are following the 2-8-8 approach. So the second shell should take a maximum of 8 electrons, right? But we are having 17 coming from the previous shell. So with that 8 electrons, we go when we update our configuration. So 2, 8, right? And on the second shell, so 8 electrons will be on the shell from our 17. Now we go again. That's 17 minus the 8 that we entered for the second shell. We're left with 9 electrons at this stage. At the second shell, we are now with 9 electrons. So we are moving on to the next shell, which is the third shell. So the third shell takes 8 electrons maximum. So every shell will take 8 electrons as maximum, right? But we are coming with how many? 9. If we are coming with that 9, we now take that 8 and update our configuration. Become 2, 8, 8 now. We are on the third shell. Now we do the subtraction. The 9 that we came with minus the 8 that we just updated becomes 1, right? It's left with 1. So now left with 1 electron more. Now since that third shell is already filled, we move on to the next one. So we are moving to the fourth shell. So that fourth shell takes 8 electrons in maximum as well. But there is just 1 electron coming from the third shell. It's only 1 electron that's coming from the third shell. So what do? This 1 electron goes into the fourth shell and the journey stops, because we are out of electrons now. So we are moving. When we go to the third shell, we are left with 1. When we come to the fourth shell, we are supposed to fill a maximum of 8, but we just have 1, and we don't have any remaining 1 again to move to any additional shell. So we stop at that point. Then what we do, we update. So it becomes 2, 8, 8, 1. So this is the electronic configuration for potassium following the 288 approach, or what we knew already before senior high school, right? This is a 288 approach. We do that 2, 8, 8, 1 becomes the electronic configuration for potassium. Now we are in senior high school. We are at the senior high school level. We don't do this method anymore. Just know that this method does not work for elements with electrons more than 20. So I use potassium, and potassium has electrons of 19. So you go to calcium, to which is has electrons whose number is 20. You can still do the 288 approach. But if I give you scandium or iron, we will have electrons number more than 20. This 288 approach cannot or will not help us. Another word is the method is not general. This 288 approach is not a general, hence does not apply in all cases, right? It was to give you an idea. That's why in junior high school we were to learn from hydrogen to calcium, which are from 1 to 20. So that you can use the 288 approach at that level. And when you come to senior high school, we don't use the 288 approach again. The thing changes, right? But then, so let's see how the thing doesn't work. So we need to actually learn the general method that works in all cases, regardless of the atom or the element, right? But before that, remember I said the shells are labeled K, L, M, N, right? So this is what goes with that. We have the shell label K, and because that's the first shell from the nucleus, right? K is the very first shell away from the nucleus, right? Or closest to the nucleus. So that's a shell number 1. So we actually count from the inside to the outside. We have to count the number of shells from inside to the outside. So the K is the first one from inside and has the shell number 1. So L has shell number 2, M shell number 3, 4, up to O shell number 5, right? This one, so we count from the inside to the outside, because the inside is the beginning one before any other one follows, right? So the shell number is N attached to that. The number of electrons on each shell follows a particular formula, general formula, and this general formula is what we have at the top here. General formula is 2n squared, where n is the shell number as seen in the table. So to know the number of electrons, the maximum number of electrons that a particular shell should actually contain, we have to use this formula 2n squared, right? So if you update our table, right, you see that the shell number K, has shell label K has shell number 1, and the number of electrons is 2, because n in this case is 1, so 2 times 1 squared is 2. So L shell also shell number 2, number of electrons will be 8 if you put it inside the 2n squared. The M is also 3, have 18 electrons in general, and 4, 32 electrons, 5, and then 50 electrons. So this is how to evaluate the number of shells that should actually be in a particular shell. This is how to actually evaluate it. And in filling of these electrons into the atom or into the shells, you need to actually start in this order. Start from the K shell, start filling from the K shell, going up or to the L, to the M, to the N. So this is the order of filling the shells within the atom following the number of maximum electrons that that particular shell should contain. So you can see that the 288 approach doesn't hold. Here is 288 in 3250. So we see that that's how the number of electrons grow, not the 288 approach. This is the basic general formula, right? So right now, from now on, we now understand that the 288 approach doesn't generally follow or that generally work, but we have an improved method that works for all elements regardless. So now on, we are going to actually understand the general method and start applying them henceforth, right? So in the next session, let's continue and understanding this general method and see how to use them as senior high school students henceforth. See you in the next session.